Good day. My name is Paulo Dalida from 4ECEB, and I will be reporting about the Bistable Multivibrator, or famously known as the flip-flops. Basically, a bistable multivibrator is a switching circuit with two output states, which is either high or low, with a denotation of Q and Q bar, which are always in the opposite states. A flip-flop is essentially a memory circuit which remains its states as is unless the inputs are toggled. Flip-flops come in SR or set or reset, JK, D or data flip-flop, T or toggle flip-flop, and etc. Let us now move further and discuss about the circuit operation and its switching theories. This is the circuit of a bistable multivibrator. It is a transistor collector coupled bistable multivibrator. This is transistor Q1 and this is transistor Q2. When Q1 is on, Q2 is off, and it acts simultaneously. It acts vice versa. When Q2 is on, Q1 is off. The circuit components of both transistors have the same values. R1, R2 are bias resistors of the transistor Q1, while R1 prime and R2 prime are bias resistors of transistor Q2. The base of each transistor is biased from the collector of the other transistor. Here we can see that the base of Q1 is biased through the collector of the transistor Q2, and base of Q2 is biased in the collector of transistor Q1. When Q2 is off, it has no collector current, and RC2, R1, and R2 acts as a voltage divider which biases Q1 through its base into saturation. When Q1 is on, its collector emitter voltage is VCE saturation or VCE sat at around 0.2 volt, and R1 prime and R2 prime biases the base of Q2 below the ground potential, keeping transistor Q2 in off condition. Here we can see capacitors 1 and capacitors 2. Capacitors 1 and 2. C1 and C2 are speed-up capacitors, which improve the switching speed of the transistors. They are commutating or memory capacitors. When Q1 is on and Q2 is off, C1 is charged to the volt across R1, and C2 is charged to the volt across R1 prime. Voltage across R1 and C1, or V capacitor 1, is greater than the voltage across R1 prime and C2, V capacitor 2. When both transistors are triggered into off state for a brief instant, VCE1, and VCE2 will approximately be equal to VCC. VBE1 will be approximately equal to VCC minus V capacitor 1, and VBE2 will be approximately equal to VCC minus V capacitor 2. Since V capacitor 1 is higher than V capacitor 2, VBE2 is greater than VBE1. When triggering voltage is removed, one transistor must begin to switch on. The one with the higher VBE, which is Q2, switches on first, and both transistors change state. Next, we go to the upper part of the circuit. Diodes D1, D2, and capacitor C3 form a circuit for negative going input signal which could switch Q1 off and Q2 on. And on the other side, diodes D3 and D4 and capacitor C4 form a circuit for negative going input signal which could switch on Q1 and Q2 off. Both diodes and capacitors form an asymmetrical collector triggering circuit. When the Q2 is off, VCE2 is approximately equal to VCC. When a negative going pulse is applied to A, D1 will be forward biased and its cathode is pulled down by delta V, while D2 will be reverse biased. VCE2 is changed from around VCC to VCC minus delta V minus VF1, where this VF1 is the forward bias voltage of across D1. C1 does not discharge instantaneously but acts like a battery. Change in VCE2 also appears at the base of Q1. The initial voltage at the base of Q1 falls by delta V minus VF1, and the base voltage is pushed below the level of the emitter voltage, causing Q1 to switch off and Q2 to switch on. Base voltage of Q1 must be below the emitter voltage within the transistor turn-off time, or T-off. This could be achieved by using a large valued capacitor, but the capacitor must be kept small as possible. D2 is used to discharge C3, while D4 is used to discharge C4. Again, D2 to discharge C3 and D4 to discharge C4 when the input is no longer present. When the input signal at A is removed and C3 is charged, C3 discharges through D2. C3 through D2. The collector resistors, the on transistors, and base resistors. This is to make sure that the voltage at the anode of D1 and D3 is approximately equal to the negative input signal when it is applied, so that the transistors could change state. In designing a bistable multivibrator, you may start from specifying the supply voltages and collector resistors. It may also start by specifying collector current. R1 and R2 must be made as low as possible to provide stable bias level, yet large enough that they do not overload RC. Same applies for on the other side. The rule of thumb that bias current passing through R2 is approximately equal to 0.1 IC can be applied. When value of RC is computed, next larger standard resistance should be selected to ensure sufficient voltage drop along RC to keep the transistor in saturation. The bias resistances R1 and R2 should be selected as the next standard size smaller than calculated so that more base current than required for saturation can be obtained. C1 and C2 must be large enough that the voltage across them will not change significantly during the turn-off time of the transistors. If the capacitors are allowed to discharge by 10% during transistor turn-off, the following equation may be used. C1 is equal to C2 is equal to T off over 0.1 R, where R is the parallel of R1 and R2. C1 and C2 limits the maximum frequency at the multivibrator, at which the multivibrator may be triggered. The maximum frequency can be computed as follows. Fmax is equal to 1 over TRE, where TRE is the capacitor recovery time, or Fmax is equal to 1 over 2.3 times capacitance times the R1 parallel with R2. On the other hand, Fmax may be given and the value of the capacitors and or resistors are then computed. Thank you for listening and have a good day ahead.